чтобы материал про компактные квантовые группы он по желанию. Вот, и экзамен не включает. Так что как скажете, лучше я совершенно не настаиваю. Okay, so at the previous lecture we made some preliminary steps towards the notion of a compact quantum group. So we understood that a compact quantum group must be a unital C-star bialgebra satisfying some special conditions. So let's recall that a unital C-star bialgebra is a unital C-star algebra A together with a comultiplication delta, which is defined to be a unital star homomorphism from A to the minimal tensor product of A by itself, such that delta is co-associative in the sense that the following diagram commutes. So we have two natural maps from A to the tensor product of three copies of A. We may compose delta with delta tensor 1. This is the identity map. And we can compose delta with one tensor delta. And both maps must be the same. So this is a unital C-star bialgebra. A typical example which actually serves as a motivation for this notion is the algebra of continuous functions on a compact topological semigroup. Compact topological semigroup. In this case, the tensor product of A by itself is isomorphic to the algebra of continuous functions on G cross G, and the co-multiplication delta is given by the following formula. So basically, this is the dualization of the multiplication on G. If we use the Gelfand-Nymark duality between compact topological spaces and unital C-star algebras, then the multiplication on M dualizes to a co-multiplication on the multiplication on G dualizes to this concrete co-multiplication on the algebra of continuous functions. And in fact, we observed that this example describes all commutative unital C-star bialgebras. So we have the following equivalence of categories. The dual of the category of all compact topological semigroups, the opposite category or the dual category, is equivalent to the category of, to the commutative part of the category of unital C-star bialgebra, C-star bialgebras. And this is the usual Gelfand-Nymark duality. So this arrow is the functor which takes G to C of G, and the opposite arrow is the maximal spectrum. And now let's recall that our goal is to construct a subcategory, to construct an interesting subcategory. Let's denote it like this. So the objects of this category will be called compact quantum groups. So this should be a subcategory in the category of all unital C-star bialgebras, in such a way that the commutative part of this category is dual to the category of compact topological groups. In the same sense as the category of unital C-star bialgebras is dual to the category of compact semigroups. So this is what we want to do now. The first approach which comes to mind here is to take the purely algebraic notion of a Hopf algebra, then to adapt this notion to the C-star algebra case, and then to define compact quantum groups as unital Hopf C-star algebras. This is the first approach which comes to mind here. And in fact, this approach, the resulting category of compact quantum groups, satisfies almost all these conditions. So in particular, we have this equivalence, with the only exception that this category is not interesting enough. The point is that there are many natural examples of unital C-star bialgebras which, for a number of reasons, must belong to the class of compact quantum groups, but which are not Hopf C-star algebras because, for example, they don't have an antipode. So this approach is not satisfactory. It leads to a very narrow class of objects. So we follow Voronovich, and we choose another approach to constructing our category. And this approach is based on the following result, which was proved at the previous lecture. Let's call it theorem 1. If G is a compact topological semigroup, then G is a topological group if and only if G is a semigroup with cancellation. The cancellation property means that if we have the following equality, x1y equals x2y, then we necessarily have x1 equals x2. So we can cancel y on the right. And similarly on the left. We have the following implication. So a compact topological semigroup is a topological group, even only if G has a cancellation property. So now, let's now dualize the cancellation property. That is, let's try to explain this property in terms of the algebra of continuous functions, in terms of C of G. And we come to the following result, theorem 2. Suppose that G is a compact topological semigroup. Let A denote. Oh, sorry. Before before I finish the statement, let me explain some notation, which is quite useful. In general, if you have an algebra A, if A is an algebra, and if you have two subsets, S1 and S2 of A, arbitrary subsets, let S1 tensor S2 denote the linear span of all elements AB, where A runs over S1 and B runs over S2. So we can now characterize the algebras of the form C of G where G is a topological group, as follows. If G is a compact semigroup and A is C of G, so as usual we denote by delta the standard co-multiplication on A given by this formula. Then the following conditions are equivalent. Condition 1, G is a topological group. And condition 2, the following two subspaces delta of A multiplied by 1 tensor A and delta of A multiplied by A tensor 1. Both these subspaces are dense in the tensor product of A by itself. Are dense in A tensor A, in the minimal C star tensor product of A by itself. So this property 2 is actually equivalent to the cancellation property of G. That is what we want to show now. To prove this result, let's first describe these two subspaces here. So it's easy to see that delta of A multiplied by 1 tensor A is the linear span. Is the linear span of all functions of the following form. Such a function takes x and y to the following number, f of xy, g of y, where f and g run over our algebra A. So this is delta of f, and this is 1 tensor g. This is 1 tensor g. And similarly, delta of A times A tensor 1 is the linear span of all functions which take x and y to f of xy, g of x, where f and g run over A. Now, to show that 1 implies 2, we simply observe that these two subspaces are star subalgebras of A tensor A. A tensor A is the algebra of continuous functions on G cross G. This is clear from these formulas. And they are easily seen to separate the points. And they separate the points. Of G cross G. Well, indeed, if you have two points, x1, y1, and x2, y2, if they are not the same, then if y1 is not equal to y2, then we can always choose G, which separates y1 from y2. And we can let f equal 1. And if y1 equals y2, that's denoted by y, and x1 is not equal to x2, then we can always find a function f which separates x1y from x2y. And again, we can let G equal 1. So this shows that these subalgebras separate the points, and so they are dense by the Stone-Weierstrass theorem. So we simply apply the Stone-Weierstrass theorem. Let's now show that 2 implies 1. 2 implies 1. So suppose these two subspaces, subalgebras are dense, and so we have to show, by theorem 1, we have to show that G satisfies the cancellation property. Well, suppose we have the following equality in G. Then, by looking here, we see that for every function h belonging to this subalgebra, we have the following equality. Just because of this, So such functions are the same on x1 and y and x2y. But by assumption, this subspace is dense in the tensor product. So this implies that the same is true. The same holds for every h in A tensor A, that is, for every continuous function h on G cross G, just by continuity and density. But this algebra separates the points, and so we conclude that x1 equals x2. So we see that G has the right cancellation property. And to get the left cancellation property, we apply the same argument to the second subspace. So similarly, we deduce that if yx1 equals yx2, then x1 equals x2. And now theorem 1 implies that G is a topological group. And this completes the proof. So this result leads naturally to the following definition due to Voronovich. It was given in 2001 and 2000, just 2000. A compact quantum group is a unital C-star by algebra, A delta, such that these subspaces are dense in the tensor product. So clearly we already have many examples. That is, for every compact group, if G is a compact group, then C of G, the algebra of continuous functions, is a compact quantum group because of theorem 2. And in fact, if we now come back to the this result, which was discussed in the previous lecture, and you restrict this equivalence to the subcategory of compact topological groups, we see that we come to our goal. So our category of compact quantum groups satisfies this condition. corollary, there is an equivalence of categories. The dual of the category of compact topological groups is equivalent to the category of commutative compact quantum groups. So this follows from theorem 2 and from this equivalence. Another useful example of a compact quantum group, which is not necessarily commutative, comes from group C-star algebras. Suppose that G is a discrete group so just a group, so we don't equip it with any topology, or alternatively we can equip it with the discrete topology. So we take the so-called left regular representation, lambda of G, on the space of square summable families on G, which takes every point x to the translation operator. So the lambda of xf is the function given by the following formula. So it translates f by multiplying the argument y by x inverse on the left. This is the so-called the left regular representation of G. And we consider the reduced group C-star algebra. So one of the equivalent definitions is that this is the C-star subalgebra of B of L2 generated by lambda of G, by the range of this representation. Alternatively, we can enlarge this set. We can replace it by a range of the respective representation of the Banach algebra L1 of G. But in fact, it suffices to consider these operators only the respective representation of G. So this is a reduced group C-star algebra of G. And I claim that it has a canonical structure of a C-star bialgebra. This is an exercise for you. I claim that there is a star homomorphism delta from the reduced group C-star algebra to the minimal C-star tensor product of this algebra by itself, which is, by the way, isomorphic to the reduced group C-star algebra of G cross G. Uniquely determined by the following formula. It takes lambda of x to lambda of x tensor lambda of x for every x in G. This star homomorphism is easily seen to be co-associative. And I claim, moreover, that it makes our reduced group C-star algebra into a compact quantum group. And the same result holds for the full group C-star algebra. C-star of G, which is defined to be the C-star envelope of the group algebra of G. So both the full C-star algebra of G and the reduced group C-star algebra of G are compact quantum groups. Our next goal is to discuss a useful subclass of the class of all compact quantum groups. Such quantum groups are called compact matrix quantum groups. Compact matrix quantum groups. And we will also discuss a typical, the most fundamental example of such an object, namely the quantum SU2 group. The quantum SU2 group. Okay, so let's start with the quantum SU2 group. So let's consider the SU2 group. So let's recall that it consists of all 2x2 matrices, complex 2x2 matrices, which are unitary. G is unitary. And unimodular. The determinant of G is 1. And we will use the well-known fact that this group can be parameterized by two complex parameters, Z and W, where Z and W are complex numbers, such that they satisfy the following condition. And GZW is the matrix of the following form. ZW minus W bar, Z bar. So topologically, SU2 is just the three-dimensional sphere. This follows from this equation. So we start with the following proposition, which will serve as a motivation for our definition of the quantum SU2. So this proposition characterizes the algebra of continuous functions on SU2 in terms of the following universal property. The algebra of continuous functions on the SU2, on the SU2 group, is the universal C-star algebra generated by two elements, alpha and gamma, such that the following matrix, alpha gamma minus gamma star alpha star, is unitary. Okay, so to prove this result, we must show that first of all, we must define two concrete elements, alpha and gamma, in the algebra of continuous functions, and to show that the respective, these elements satisfy the respective universal property. So we define alpha and gamma as follows. Alpha and gamma, they are continuous functions on SU2. So alpha takes every element, every matrix to the upper left corner, which is Z, and gamma takes this element to W. Clearly, they are continuous functions. So let's denote the respective matrix by U. U is alpha gamma minus gamma star alpha star. So this is a 2x2 matrix over our algebra of continuous functions. By the way, why is it unitary? Well, the easiest way to answer this question is as follows. We identify the matrix algebra over the algebra of continuous functions with the algebra of continuous functions, of matrix-valued continuous functions on SU2 in the obvious way. And under this identification, this matrix U corresponds to the inclusion map. Inclusion map of SU2 into M2. Just because of the concrete formula for this matrix. Well, this inclusion map is clearly a unitary element because for trivial reasons, every matrix in SU2 is unitary. So this implies that U is unitary. U is unitary. And now we have to show that these elements, alpha and gamma, satisfy the respective universal property. So we suppose now that alpha is a unital C-star algebra, and alpha and beta are A and B are two elements of A, such that the following matrix alpha AB minus B star A star is unitary. If we try to write this condition explicitly, I mean the condition that this metric is unitary, we come to the following result, and this is a little calculation which I leave as an exercise for you. This matrix is unitary if and only if the elements A, B, A star, and B star commute. They commute, and A star A plus B star B equals 1. This is proved by an explicit calculation. So what we want to do now is to construct a star homomorphism from our algebra of continuous functions to A, which takes alpha to A and gamma to B. Well, since these elements commute, so if we now let B denote the C-star subalgebra of A generated by A and B, then it follows that B is a unital commutative C-star algebra. B is commutative and unital. So it's natural to take the maximal spectrum. Let X denote the maximal spectrum of B, which is naturally identified with the character space. And we observe that for every character chi of B, we have the following relation. So this is obtained by applying chi to this equation. We simply apply chi to this, and we get this. Therefore, we can now define a map, which is clearly continuous, that's denoted by F, from X to SU2, which takes chi to the matrix GZW, where Z is chi of A and W is chi of B. So chi of A and chi of B satisfy this condition. So the respective matrix is indeed an element of SU2. Let's now dualize this map. So this map gives us an algebra homomorphism. So the algebra of continuous functions on SU2 is mapped to the algebra of continuous functions on X by means of f dot. So as usual, f dot takes every element A to A composing with f. C of x is isomorphic to B by means of the Gelfand transform. This is the inverse of the Gelfand transform. And B is a subalgebra of A. So if we now compose these arrows, we get a star homomorphism from C of SU2 to A. We denote it by phi. And a simple calculation, again this is an exercise for you, shows that phi is exactly what we are looking for. It takes alpha to A and gamma to B. And formally, to complete the proof, we have to prove that such a homomorphism phi is unique. So the uniqueness of phi, well, this is immediate from the fact that the star subalgebra of the algebra of continuous functions on SU2 generated by alpha and gamma is dense. The star subalgebra of C of SU2 generated by alpha and gamma is dense in C of SU2. As usual, by the Stone-Weierstrass theorem. Clearly, these two functions, alpha and gamma, they already separate the points. And so the subalgebra generated by these two elements is dense by the Stone-Weierstrass theorem. And this completes the proof. So we have proved that the algebra C of SU2, together with these two concrete functions, alpha and gamma, satisfies the respective universal property. So we get this isomorphism. Okay, so this proposition leads to the following definition due to Voronovich. If I'm not mistaken, 1987. Suppose that Q is a real number between -1 and 1 and different from 0. Then we define the algebra of continuous functions on the quantum SU2 group well, let me put the quotation marks here, because of course this algebra is not an algebra of functions, it is not commutative. But here the terminology is inspired by the general philosophy of non-commutative geometry, which states that non-commutative C-star algebras can naturally be considered as algebras of functions on non-commutative compact spaces. So the algebra of continuous functions on the quantum SU2, or briefly just the quantum SU2, is the following C-star algebra. It is denoted like this, CQ of SU2. And another standard notation looks as follows, CUQ of 2. And by definition, this is the universal C-star algebra generated by two elements alpha and gamma, such that the following matrix alpha gamma minus Q gamma star alpha star is unitary. Well, if we compare this definition with our previous result, we conclude that if Q equals 1, then what we get is just the algebra of continuous functions on SU2. if Q equals 1, then this algebra is just the algebra of continuous functions on SU2. So we get a whole family of unital sister algebras parameterized by the number Q. And in fact, this family can be interpreted as a kind of deformation of the algebra of continuous functions on SU2. And this algebra itself is a kind of the limit of these algebras as Q tends to 1. This informal observation can be made into a theorem, which is not trivial, by the way, but this involves a rather involved theory, a rather complicated theory due to Mark Riffel. This theory is called strict deformation quantization. But this is a rather different story, so unfortunately we don't have time to discuss these results. But anyway, informally, these algebras form a continuous family of sister algebras parameterized by Q. And if Q equals 1, then we get a commutative object, the algebra of continuous functions on SU2. Okay, but so what is the problem here? At this point, the quantum SU2 is just a unital sister algebra. So we want it to be a quantum group, a compact quantum group. But so far, it's just a unital sister algebra. So now our goal is to introduce a co-multiplication on this algebra and to show that this co-multiplication satisfies our density conditions, that it satisfies our definition of a compact quantum group. In fact, the construction of a co-multiplication is rather straightforward, but the proof of the density condition is not so easy. And to prove these density conditions, it will be useful to discuss this in a rather general setting, also due to Voronovich. So we will use the following notation. Suppose that A is a unital star algebra, and suppose that U is a matrix, an n by n matrix with entries in A. We define two matrices, U transpose and U conjugate, in the same algebra, Mn of A, as follows. So U transpose is just the usual transpose, so its ijth entry is uji. And the conjugate matrix U bar is obtained by applying the involution to every entry of U. So this is Uij star. U bar ij is Uij star. And then I'll give the following definition, also due to Voronovich. This is 1991. So it was given later than Voronovich introduced his quantum SU2 group, but before he introduced the general notion of a compact quantum group. In some sense, this definition is the first version of the notion of a compact quantum group. A compact matrix quantum group, and we will use the following abbreviation, is a triple A delta U, where A is a unital C-star algebra, delta is a star homomorphism, a unital star homomorphism from A to A tensor A, a unital star homomorphism. And U is an n by n matrix over A, such that the following conditions are satisfied. First of all, we claim that both U and U transpose are invertible matrices. This is condition 1. Condition 2 is that A must be generated by the matrix entries of U. A is generated by the elements Uij for all I and j between 1 and n. Well, I mean generated as a C-star algebra, as a unital C-star algebra. That is the smallest C-star subalgebra of A containing, the smallest unital C-star subalgebra of A containing these elements is A itself. And condition 3 explains how delta acts on the matrix entries. Delta of Uij is given by the following formula. This is the sum over K, delta Uik tensor Ukj for all I and j. So I claim that every compact matrix quantum group is a compact quantum group. So we have the following theorem. If A delta, oh, sorry, before we prove this result, let's look at an important example which explains the terminology and which explains where this definition came from. Suppose that G is a closed subgroup of the unitary group Un, a closed subgroup. As usual, Un is the group of all unitary n by n matrices. So G is a compact topological group, and in fact, it's the standard result from Lie theory that it's a Lie group. So we denote by A if we consider the algebra of continuous functions on G. And we define U, the n by n matrix over A, by the following simple formula. Uij is just the respective coordinate function on G. It takes G to the ijth coordinate of G. Well, as just like in the case where G is SU2, we observe that G is unitary. So we may identify Mn of A with the algebra of continuous functions on G with values in Mn, and we observe that under this correspondence, U corresponds to the inclusion map of G into Mn. So so U is unitary. In particular, it is invertible. If we look at U transpose, well, U transpose is unitary more or less for so U is unitary, so it is invertible. U is invertible, and for the same reason, U transpose is invertible. Similarly, U transpose is also invertible. Well, because U transpose corresponds to the function which is obtained from U by transposing the matrix entries of the respective functions, of the respective matrix. Of course, if we take the transpose of an invertible complex valued matrix, then the transpose matrix is also invertible. The fact that A is generated by the matrix entries is immediate from the Stone-Weierstrass theorem. Stone-Weierstrass theorem implies that A is generated by Uij. Because these elements separate the points clearly of G, and so the star subalgebra generated by these elements is dense. And finally, to prove condition 3, we do a simple calculation, delta of Uij. Delta of Uij. This is a function of two variables, so we apply it to x and y. This is, by definition of our delta, this is Uaj applied to xy. But U is, so this is just the ijth coordinate of xy. And so this is the sum over k, x, I, k, y, k, j, the usual formula for the matrix multiplication. But this is nothing but the element uik tensor ukj applied to x and y. And so we see that condition 3 is also satisfied. In fact, condition 3 is nothing but the dual way of writing the matrix multiplication. So we deduce that C of G, together with delta and U, is a compact matrix quantum group. In fact, there is a theorem which states that all that all commutative compact matrix quantum groups are always foreign. But this is not trivial at all, because if we look at the definition of a compact matrix quantum group, so we don't assume here that U is unitary. So if we start with a commutative compact matrix quantum group, it is not trivial that it arises in this way. But this is indeed true, and if we have time, we'll prove it later after we discuss some basic facts on co-representations of compact quantum groups. In some sense, compact matrix quantum groups can be interpreted as compact quantum Lie groups, because in the classical situations, compact Lie groups are just closed subgroups of the unitary group. Okay. So let's now prove that every compact matrix quantum group is indeed a compact quantum group. If we start with a compact matrix quantum group, then A, together with delta, is a compact quantum group. First of all, we observe that properties 2 and 3 easily imply that the co-multiplication is co-associative. Two and 3 imply that delta is co-associative. Formally, this is a little calculation, and I'll leave this as an exercise for you. So the co-associativity axiom should be proved only on the star generators only, and for the star generators, this is immediate from this formula. So what is not entirely trivial is the density conditions for A and delta. The proof will be divided into several steps. So lemma 1. Let B denote the set of all elements A in A such that delta of A belongs to such that A tensor 1 belongs to delta of A 1 tensor A. And I claim that B is a unital subalgebra of A. Well, why is it so? First of all, it's clear that B is a vector subspace. Of course, it's a vector subspace of A, and it contains the identity, because delta is a unital homomorphism. So we have to show that the product of two elements in B belongs to B. We'll suppose that A and A prime are two elements of B. So by assumption, A tensor 1 can be written in the following formula as the following sum, a finite sum over, say, I, delta of AI, 1 tensor BI. And similarly, A prime tensor 1 can be written as a finite sum, delta of AI prime, 1 tensor BI prime. Or it's better to use another index that's denoted by J, sum over J. So let's multiply these two expressions. A prime tensor 1 is just the product of A tensor 1 and A prime tensor 1. So A tensor 1 is the following sum over A over I, delta of AI. And here let's observe that we can interchange this and this. So these two elements commute. So this can be written as delta of AI, A prime tensor 1, 1 tensor BI. Now we substitute now this expression for A prime tensor 1 here. So we get the following double sum over I and J, delta of AI, delta of AJ prime, 1 tensor BJ prime, 1 tensor BI. And as a result, we see that since delta is an algebra homomorphism, we see that this is the sum over I and J, delta of AI AJ prime times 1 tensor BJ prime BI. And this clearly belongs to the same subspace. And that's it. So this shows that the product A prime belongs to B. So B is a unital subalgebra. Lemma 2 states that B contains all elements of the form Uij. So all the matrix entries Uij belong to B. Uij belongs to B. And the same is true for the adjoints. Uij star belongs to B for every I and J. Well, let's start with Uij. Let V denote the matrix, the inverse of U. Да, да. Та же самая algebra. B is the same algebra which was introduced in lemma 1. So let V be the inverse of U. And let's look at the following element. The sum of delta uik multiplied by 1 tensor vkj, the sum over k. So what's this? Delta of uik is the sum over L, so we get the double sum over k and L. UIL tensor UL k, and here we also multiply by vkg. Okay, now V is the inverse of U. So if we now take the sum over K, we see that this is just the Kronecker delta by the usual formula for the matrix multiplication, delta Lj. And then we take the sum over L, and we get what we get. We get to Uij tensor 1. But this element belongs to B, of course. And so we deduce that this element, well, this element belongs to our subspace delta of A tensor 1 tensor A, and so this implies that Uij belongs to B. Now we have to show that Uij star belongs to B. Let's observe now that if we take the conjugate matrix U bar, then this is nothing but U transpose star. So the adjoint of U transpose is just U bar, the conjugate matrix. So we conclude that U bar is also invertible. And now we can apply the same argument to U bar and deduce that Uij star belongs to B. We apply the same argument to U bar instead of U and deduce that Uij star belongs to B. And this completes the proof of lemma 2. Okay, now we are ready to prove the density conditions, which appear in the definition of a compact quantum group. And of proof of theorem. So lemma 2 implies that B is dense in A. Well, indeed, by assumption, A is generated by the matrix entries as a star algebra. As a C-star algebra is generated by the elements Uij, but these elements and the adjoints belong to B, and so B is dense in A. Now, if we take an element B, little b in our subalgebra B, and an arbitrary element A in the algebra A, let's look at B tensor A. So this is just the product of B tensor 1 and 1 tensor A. B tensor 1 belongs to a delta of A multiplied by 1 tensor A. Belongs to the subspace. 1 tensor A also belongs to one tensor big A, clearly. So as a result, we see that this is nothing but delta of A times 1 tensor A. And so the space delta of A 1 tensor A contains all elements of this form. So we see that delta of A 1 tensor A contains B tensor A, the algebraic tensor product of B and A. But B is dense in A. And so this algebraic tensor product is dense. This is dense in the C star tensor product of A by itself. This is even bigger, so this is also dense. So this proves one of our two density conditions. And the proof of the second density condition is an exercise for you. It is proved by more or less the same argument. Delta of A times A tensor 1 is also dense. So this implies that indeed A and delta is a compact quantum group. Okay. Okay, let's now come back to the quantum SU2. So as before, we take a real number q between -1 and 1, a non-zero number q. And we define the unitary matrix U, which appears in the definition of the quantum SU2. That is alpha gamma minus q gamma star alpha star. This is the 2 by 2 matrix with entries in the quantum SU2. So let's recall that the quantum SU2 was defined as the universal C-star algebra generated by alpha and gamma, such that this matrix is unitary. So first of all, I claim that the defining relations for the quantum SU2 are as follows. So if we explicitly write the condition that this matrix is unitary, we get the following. Alpha gamma is q gamma alpha. Gamma is normal. Gamma star gamma equals gamma gamma star. Alpha and gamma star also commute up to q gamma star alpha. Alpha is not, we also have the following relation between alpha star alpha and gamma star gamma, which is, in this case, it looks exactly is in the non-quantum SU2 group. And finally, if we interchange here alpha and alpha star, we get something different. Alpha alpha star plus q squared gamma gamma star is 1. So these are the defining relations for our quantum SU2 group. Now, part 2, there is a star homomorphism, delta from A to A tensor A, where A is our algebra, CQ of SU2, uniquely determined by the following formula. Well, basically by the formula which appears in the definition of a compact matrix quantum group. Delta of Uij equals the sum over K. Now this sum has only two summands from 1 to 2. Uik tensor Ukj. So that is explicitly, this means that delta of alpha is alpha tensor alpha minus Q gamma star gamma. And delta of gamma, again by using the matrix multiplication, usual matrix multiplication, this is gamma alpha, gamma tensor alpha plus alpha star tensor gamma. So these two formulas completely determine our star homomorphism delta. And part 3, I claim that A, delta, and U is a compact matrix quantum group. Compact matrix quantum group. So in particular, we deduce that the quantum SU2 is indeed a compact quantum group, because it is a compact matrix quantum group. The proof of parts 1 and 2 is an explicit calculation. And this is, again, a simple exercise for you. Just write explicitly the condition that U is unitary, that is U star U equals 1 and U star equals 1, and get these conditions. This is quite straightforward. To prove the existence of such a star homomorphism, we just use the universal property. So we have to show that this element, and this element belonging to A tensor A satisfy the same commutation relations. So if we denote it by, say, S and T, then show that S and T satisfy the same commutation relations as in part 1, and use the universal property of our algebra. So finally, to show that this is a compact matrix quantum group, the only thing to be shown is that the transpose matrix, U transpose, is also invertible. And this is a little trick. We take a complex number lambda such that lambda squared equals lambda squared equals q, just q. If q is real, if q is positive, then lambda is also positive. If q is negative, then lambda is imaginary. And show that if we multiply the conjugate matrix U bar by the following matrix: 0 minus lambda, lambda inverse 0 on the left, and 0 lambda minus lambda inverse 0 on the right. Then what we get is just here. This is again a little calculation by matrix, so just use the usual matrix multiplication. So since U is invertible, and these two matrices are also clearly invertible, this implies that U bar is invertible. U bar is invertible. And we already know how U bar and U transpose are related. So U transpose is U bar star, U bar joint, and so U transpose is also invertible. And that's it. So we see that the quantum SU2 is a compact matrix quantum group. So in particular, it is a compact quantum group. Okay, so that's all for today. At the next lecture, we briefly consider some other examples of compact matrix quantum groups, and then begin discussing the Haar state on a compact quantum group. So it's a classical result due to Haar and von Neumann, and also to André Weil, that for every locally compact topological group, there is a left invariant measure, a left invariant Borel measure, positive Borel measure on the group, the so-called Haar measure. For compact groups, this was proved by von Neumann, and for general locally compact groups by André Weil. So we will prove a similar result for compact quantum groups. So in this case, measures will be replaced by states, because the state on the commutative C-star algebra is just a positive random measure. And we will show that there is, for every compact quantum group, there is a distinguished state on this on the respective C-star algebra, which use a nice left and right invariance property. So this is the so-called Haar state. Okay, thank you.